All right, Assalamu alaikum. So in the previous lecture, we looked at a quantum algorithm, the Deutsch algorithm. So I would like to spend 5 more minutes on recapping this algorithm. All right, very briefly. In the Deutsch algorithm, it's an incredibly useless algorithm, but it actually shows the power of quantum information. The idea of this algorithm is that it maps a decision problem onto a quantum circuit. All right, please, no commotion, please, attention here. So if I were to redraw the circuit for the Deutsch algorithm, this is what it looks like. I have 2 qubits, one qubit initialized in the state ket 0, the other qubit initialized in the state ket 1. Each one of these qubits then sees a Hadamard gate, which is a unitary operator. It creates superpositions. This is followed by a controlled operation on the second qubit, UF. We've defined what UF does. And the UF conditionally applies the function onto the second qubit in a particular fashion. Finally, we have a Hadamard gate here. We don't really care about what happens to this qubit, so we don't care about it from this point onwards, but it's extremely crucial that we keep the qubit up till this state. We don't look at it any further, but without this qubit we will not be able to do the algorithm. At this point we get 2 possibilities at the output. One of these possibilities is a ket 0, the other possibility is a ket 1. So we do a measurement here. So we measure the state of this qubit, and how do we do a measurement? We have some kind of device that creates 2 channels, a ket 0 channel and a ket 1 channel, like a beam splitter or a polarizing beam splitter, whatever the case may be. If this detector clicks, we have one property of the function f, and if the other detector clicks, we have the other property of the function f. So f can be of 2 kinds. The function f can be constant, or it could be balanced. And we have 2 scenarios within each realm. 2 kinds of constant functions, 2 kinds of balanced functions. Classically, we would like to, if we were to ask the question, what is f, what kind is it, whether it's constant or balanced, you would have to do the experiment twice. But in quantum computing, you can just do the experiment in one go. With 2 qubits, you can tell by looking at just one qubit, and the outcome of that qubit you can tell and make a decision of whether the function is constant or balanced in one shot. If you had a big function which acted, say, on 8 bits, then you would just need 3 qubits going into your quantum computer, and you could tell whether the function is constant or balanced in one go. So from 8 you can go to 3 qubits, for 16 you can go just to 4 qubits, you get exponential speed up. So this is the basic idea of a quantum algorithm. So first of all, how a quantum algorithm generally works, you feed in certain initial states. These are your initial quantum states. Then somehow you would like to create a superposition. Here you create a superposition. That's what these Hadamard gates do. You create a superposition. So some kind of superposition is created here. Finally, there is some correlation between the 2 qubits. Those superpositions are adjusted in such a way that some elements in that superposition pick up a minus sign or some phase. That's what this controlled function does. Finally, you have a superposition, but you can't measure superposition. So you need to divert them back into basis states, ket 0 and 1, so that you can make certain measurements. So you have the superposition, everything then collapses together, and you get an eigenbasis or a basis state ket 0 or ket 1 here, and which basis state do you get depends upon the kind of function. So even though we cannot measure superpositions, you map and encode your algorithm in such a fashion that the two orthogonal outputs, each one of them corresponds to one kind of function, and you're able to make a decision. So this is the process of encoding an algorithm into a quantum, encoding a problem into a quantum algorithm. That's the gist of it. All right. So any big questions about this? So in our previous lecture, we did the quantum state progression step by step. We looked at the state over here, the state over here, the state over here, given we know the truth table of this controlled function. Finally, we looked at the state over here, and we found out that if the function, if I don't precisely remember, if it's constant, one of the outputs is going to be populated. If the function is balanced, the other output is going to be populated. All right. So the function is constant. There's constructive interference taking place on this path and destructive interference taking place on this path. So this is the general scheme of a quantum algorithm. All quantum algorithms, factoring algorithm, the algorithm to find discrete logarithms, optimal path finding algorithms, Grover's search, quantum Fourier transforms, all kinds of quantum algorithms follow this general rule. By the way, if you look at a Michelson interferometer, sorry, a Mach-Zehnder interferometer, that's also a quantum computer. And if you were to draw the quantum circuit for a Mach-Zehnder interferometer, this is really what it looks like. A Hadamard gate, which is your first beam splitter, followed by a controlled phase gate, which gives you the possibility of adjusting the phase of one of the paths so that you can get interference. And finally, another Hadamard gate, which is your second beam splitter. So this circuit overall shows a Mach-Zehnder interferometer in quantum circuits language. It's the same thing. The Mach-Zehnder interferometer gives you a physical feel of what the hardware is going to look like, mirrors, beam splitters, photons coming in, but a physicality independent description would look like this. So all of quantum information processors work in this fashion. You have some initial quantum states, you have a transformation, you must have the ability to do quantum gates which process the information. You should have the ability to measure quantum states, and you should protect your quantum computer from the environment as well, so that these states are not collapsed before they are intended to be measured. So all of this needs to work together. Yes, please. So समझ आना के कोई ऐसी बात नहीं. So this is how this works. Get x, get y. This is your input to this gate. It leaves the first qubit unchanged, and the second qubit takes up a new value, 0 or 1, and that value equals y, this value, which originally was in the qubit, exclusive OR with the function acting on x. Right, so this is how this gate works. Yes, so this has two inputs. This is the first qubit, the second qubit. It has two outputs, the first qubit, the second output. So if this were x, this were y, nothing happens to the first qubit, but the second qubit takes up a value y, exclusive OR with function acting on x. Alright? ये आगे चला जाएगा. ऊपर कुछ नहीं जा रहा, ये x आगे जा रहा है और ये वाला qubit इधर जा रहा है. सिर्फ ये जाएगा. अभी ये पिछले लेक्चर के नोट्स देखना, फिर वो मेरे क्लास में आना कि पिछले लेक्चर में इसको हाथ से करो खुद. ठीक है, आपका सवाल था कोई इधर? Any more questions? So all of these quantum circuits, these are really quantum computers or quantum information processors. They are built up of these qubits. These qubits carry on these hypothetical wires like a normal computer. Then you have gates of different kinds. For example, you have Hadamard gate, you can have a phase gate, you can have a NOT gate, you could have, say, an X gate, a Y gate, a Z gate, a rotation gate. Different kinds of gates are possible. So this is a library of gates that are available to you. In any algorithm, you have libraries of functions available. So these are libraries of gates, and each one of these gates, by the way, that I've drawn over here is an example of a single qubit gate. One qubit comes in, one qubit goes out. This is an example of a 2 qubit gate. 2 qubits come in, 2 qubits go out. So what is this an example of? Is this a 2 qubit gate or a single qubit gate? This is not a genuine 2 qubit gate. These are 2 single qubit gates, but they can be treated like a 2 qubit gate. But there's no correlation between what happens between the first qubit and the second qubit. So each one of these gates, by the way, can be represented by a matrix. What would be the size of this matrix? Any ideas on the size? How big would it be? 2 by 2. So what would this matrix look like? 0, 1, 1, 0. This is also 0, 1, 1, 0. So these are the same thing. This is generally a Y gate. A Z gate is 1, 0, 0, minus 1. This is a phase gate in disguise with a phase value of pi. So this is the same as this phase gate, but sorry, this is H. This is a rotation gate. We've already seen a rotation gate, cosine theta, minus sine theta, cosine theta. All of these gates, by the way, represent some kind of rotation, and I might explain this in a later class. So this is the library of gates that are available to us, and we can choose and pick from this library of gates and build up our quantum circuit. So the real task of an algorithm designer is to map the logical problem onto the quantum circuit, map it onto the qubits, map it onto the gates, and so on. So collapse generally hurts us. When we measure a superposition, the superposition goes away, right? So the collapse is not something that is generally thought to be of an advantage. So we bypass this disadvantage. We circumvent this disadvantage by designing our algorithm in such a way that the collapse into orthogonal states gives us answers to the question that we're seeking an answer to. All right, yes, please.
For that, the circuit we made for the interferometer.
Sorry?
The circuit that we made for the Mark Center interferometer, why did we use a phase gate? हमने mirrors के not gate use किए क्या? Purpose of the mirror.
To कर लो. So if you put 2 NOT gates back to back, you can still add the NOT gates, fine.
Oh, अच्छा. Oh, sorry.
You can still do that. In your homework problem number 2, there are some more problems that deal with quantum gates, both in matrix notation as well as ket notation. So now I would like to introduce the idea of entanglement. In order to introduce the idea of entanglement, let me first show you a circuit that makes an entangled quantum state, and then I'll describe what is really meant by an entangled state. So this deserves some special attention. The Nobel Prize in Physics 2 years ago was awarded to 3 scientists who worked on entanglement and the violation of Bell's inequalities. Baatein na karen, please. Now suppose I draw a circuit, a quantum circuit with 2 qubits, and I place a Hadamard gate on the first qubit, UH, followed by a controlled NOT gate with the first qubit as the control and the second qubit as the target. and I feed in ket 0 on the first channel and ket 0 here. So my input state psi in is ket 0 crossed with ket 0. This is the first qubit, second qubit, or in short I can write this as ket 0 0. So what I would like you to do in the next 2 or 3 minutes is find the state over here, the state over here, and please indicate what the final state is going to be after this input has propagated through this circuit. Please compute the output quantum state. So what's the state over here? You just create a superposition out of this. So you have 0 plus 1 ket, this is the first qubit, the second qubit is still ket 1, sorry, ket 0. So this is 1 over under root 2, 0 0 plus ket 1 0. Now you would like to do a control not on this state. So the state that you get over here at this point, you look at this input and invert the second qubit and the first qubit is in a state 1. So you would get 1 over under root 2 ket 0 0 plus ket 1 1. Right? Pretty straightforward. Now if you look at the inputs that I have, this input state is ket 0 for the first qubit and ket 0 for the second qubit. So I can define what the state of the first qubit is and what the state of the second qubit is. Alright. However, for this output state, if I were to ask you the question, what is the state of the first qubit and what's the state of the second qubit, will you be able to give an answer to this? Not exactly. This state cannot be factorized into some state on the first qubit and some independent state on the second qubit. Any quantum state psi which cannot be written as ket phi some state on the first qubit tensor with some state on the second qubit, any state that cannot be written in this fashion is called an entangled state. This is an example of an entangled state. Yes, please. I'll repeat. This is just the first introduction. I'm going to spend 10 minutes on this. So this is the basic definition of an entangled state. So let me give you some counter examples. Suppose I write a quantum state 1 over under root 2, a normalization constant ket 0 0 plus ket 0 1. Now I can factorize this to, first of all, is this a 2 qubit state? 2 qubit. It's a superposition state as well because of this sign over here. Now what I could do, I could factorize out the character of each qubit. This state is totally equivalent to ket 0 crossed with 1 over under root 2 ket 0 plus ket 1. So I've taken this state and I've just written in a factorizable form in which the identity of the first qubit is clear. This first qubit is in a state ket 0 and the second qubit is in a superposition state. All right. Now this could be, for example, an example for this could be if I'm looking at a photon and I'm looking at the path and the polarization of a photon, this could be ket 0 H plus ket 0 V, over under root 2. What this means is ket 0 tensor product with H plus V. Right? So the second qubit, suppose, is the polarization degree of freedom. The first qubit is the path degree of freedom. So this would really mean that the photon is along the path ket 0 and it is diagonally polarized. So I can assign an identity to the first quantum degree of freedom or the first qubit and an identity to the second qubit. In other words, I can take this state and factorize this into states for each of the two qubits. This is an example of a separable state as in opposition to an entangled state. What about if I were to take a state ket 0 0 plus ket 0 1 plus ket 1 0 plus ket 1 1? Is this entangled or separable? Can I write this as a tensor product of two kets? If I am able to write this as a tensor product of two kets, this is not an entangled state, rather it's a separable state. Can I write this as a tensor product of two kets? I can, in fact. If I were to write this as 1 over under root 2 ket 0 plus 1 tensor product with 1 over under root 2 ket 0 plus 1, if I were to expand this, this would come out. So this indeed is a separable state because I can express this as a factorizable tensor product of two qubits, states of two qubits. Yes, please.
Sir, how exactly do you figure out if the state is factorizable?
Well, you just have to work it out. How do you factorize out an algebraic expression? Well, this is evident. I mean, some practice and some insight. This is what physics is all about. Yes, please.
What if there are more qubits, more than two qubits?
Well, we'll look at this. Yes, please.
So isn't that a separable state?
Which one? This one? This is separable, yes. So this is an example of a separable state. However, if I were to consider this output from this circuit, is it possible to write this particular combination as a factorizable product of two qubits? I cannot do that. It's impossible to do that. There's no way I can write this as a ket tensor with another ket. It really is this thing here. Let's call this state psi out. This quantum state here is really 1 over under root 2 ket 0 tensored with ket 0 plus ket 1 tensored with ket 1. So it's a sum of separable states. So it's a sum of, this is a factorizable state, it's another factorizable state, but when I take the superposition of these factorizable states, the net 2 qubit state, which is this big state, is no longer factorizable into one qubit tensored with another qubit. I cannot write this state in this fashion, no matter what phi or chi I choose. So this is an example of an entangled state. Yes, please.
वो येलो वाली लाइन से हम लोगों ने आगे जाके वो आई कैसे है वो आउटपुट
ये वाली
हाँ जी
देखो ना, if this is our state, we want to apply control not to it. So control not is changing the second qubit when the first qubit is 1. First qubit is 0, nothing happens. First qubit is 1, the second qubit is inverted. So this is how you get this output. So let's write other examples of entangled states. Can you give me a few more examples of entangled states for 2 qubits? Yes. Let's use 0 1 notation. Ket 1 0. Excellent. This is another example of an entangled state. Very nice. So this cannot be written in separable form. It cannot be factorized as one qubit times another qubit. Likewise, if I put minus sign here, this is also an entangled state. Plus 1 1 minus sign is also an entangled state, either plus or either minus. So all four of these states are examples of entangled states, and they're maximally entangled. They are the most entangled states that you can get for 2 qubits. Maximally entangled states, and they have a special name. They are called Bell states. And one generally uses a special symbol for the Bell states. One calls these states phi, big phi, plus or minus, and these states big psi, plus or minus. So there are 4 kinds of Bell states which are entangled states for 2 qubits. Now we've seen a process, a kind of circuit that creates a Bell state. So you have a separable input and you have a Hadamard gate followed by a controlled operation that creates a Bell state. Now Bell states have the 2 qubits, they are intertwined in a really strong fashion. They have extremely strong correlations, as I'll explain in a minute. In order to create those correlations between the 2 qubits, you need to have some kind of gate that correlates the 2 qubits. So you need to have a controlled operation. 1 qubit operations on separable states cannot create a Bell state. So you need a 1 qubit operation followed by this controlled gate which creates correlation between the 2 qubits. Reason is creating a correlation because it changes 1 qubit by looking at the other. So it creates a correlation. So this circuit that you have here creates a Bell state. It's a Bell state generator circuit. What if I feed in, instead of ket 0, ket 1, what if I feed in ket 1 crossed with ket 1? What would be the output state? So if I were to feed in into the Bell generator circuit, U Hadamard followed by a controlled NOT gate, and now I feed in ket 1 crossed with ket 1, which is a separable state. What would my output be?
0 1 minus 1 0.
So my output would be psi minus, which is 1 over under root 2 0 1 minus 1 0. So these are examples of entangled states. Now why are entangled states important? Because they cannot be explained classically, number one. They lead to measurement outcomes that totally defy our common sense, as I'll show in a minute. They are the hallmark of quantum physics. There is no classical analog to these states. And let me show you how. Any questions up till this point? Yes, please.
Shouldn't that the other state be 1 1 minus?
No. I think this is correct. Now suppose I have an entangled state. There was a question about higher number of qubits. Who asked that question? Yes. Can you give me an example of a 3 qubit entangled state? Pretty easy.
Horizontal, vertical, diagonal.
Diagonal is not. Diagonal is a combination of horizontal and vertical. All right, 0 0 1. That's it. 1 1 0 1 0 0. It's 1 1 0. This is an example of a 3 qubit entangled state. If I were to put a 0 here, suppose if by the way, this needs to be normalized as well. If I were to put a 0 here, for example 0, 0, 1 plus 1, 0, 0, is this factorizable? If I look at the second qubit is always in the state ket 0. So the first and the third qubits are entangled, but they're separable from the second qubit. Right? And the first and the third qubits, they are in a state 0, 1 plus 1, 0, which is a Bell state, one of these Bell states. So I can write this state as ket 0 tensored with psi plus. But now I need to identify, the ordering has been kind of muddled up a little bit. I need to identify this is my second qubit, which is in between, and the first and the third qubits are now entangled with one another. So I just write 1 and 3 over here just to make this distinction. The first and the third qubits are entangled, and the second qubit is separable from the other two. So this is not a completely entangled state, it's a partially entangled state. But this is a completely entangled state. Another example of a 3 qubit completely entangled state or maximally entangled state is with a minus sign perhaps or plus sign, both of them work. This is called GHZ state. Greenberger Horn Zeilinger state. GHZ state, okay? Yes, please. There's a plus sign here, so plus corresponds to this plus because of this plus. नहीं आपको कंट्रोल नॉट तो नहीं कर रहे. Alright, so you can have entanglement in 3 qubits, 4 qubits, 2 qubits, complete, partial. So it's a fascinating subject. So what does entanglement mean? So the idea of entanglement was first proposed in 1935, way back in 1935, by Einstein, Podolsky and Rosen, 3 scientists, EPR. This effect is also called the EPR effect. And Einstein was really uncomfortable with the idea. He thought that his prediction of entanglement means that quantum physics is yet incomplete. There is something missing in quantum physics that we don't really know about. There's something hidden. So he thought that quantum physics was incomplete, and he never liked quantum physics for the same reason, even though he was one of the discoverers and inventors of this body of knowledge. So what's so confounding and baffling about these entangled states? So let me try to explain this, and I also have one colorful slide that does that. Suppose I'm talking about photons as my system of choice, and I'm talking about the polarization of photons. So if I were to talk about the polarization of photons, one of the possible Bell states is HH plus VV. Right? So this is a Bell state corresponding to 0, 0, ket 0, 0 plus ket 1, 1. A Bell state, 2 qubits. Got it? Now these photons, so how many photons are we talking about? We're talking about 2 photons. It's a 2 qubit state. This is my phi plus state. It's a 2 qubit entangled state or Bell state. One of the 4 canonical Bell states. It's a Bell state. Now these photons can be generated as an entangled pair, and we do this in our laboratory. So in this class, in one of the classes, I'm going to invite one of my colleagues, in fact one of our former students, who's going to give you a picturesque tour of what such a lab looks like. So so one way of creating these photons is you have these special crystals. These are BBO crystals. BBO stands for barium borate. Barium borate crystals, beta barium borate crystals, and you shine light on these crystals. In a particular polarization, and emerges two beams. Two beams emerge from the crystal. Two beams come out. So one photon is in this beam, the other photon is in the other beam. And both of these photons have their polarizations entangled with one another. So the state of these two photons is phi plus. So now there are two photons coming out from this crystal. We have generated an entangled pair of photons. Two photons come out and they are entangled. Their polarization degrees of freedom are entangled with one another. Alright, so somehow we have created this entangled pair of photons. And now they are correlated with one another in a really strange fashion. So what I do next is I take these two photons and kind of change their orientations a little bit. So one photon goes here and the other photon goes to the other side. And we're talking not about the paths of the photons, we're talking about the polarization degree of freedom. So now one photon goes to one party. Let's call this party Alice. This is convention in quantum information science. The other party is called Bob. And Alice and Bob can be really, really far apart. They could be on different parts of the earth, different laboratories, different nooks and corners of the SSC building, different planets. They could be very far apart. Now they have different photons. Alice has one photon and Bob has another photon. But both of them are entangled with one another. Both photons are entangled because they share this kind of ghost-like correlation amongst themselves. Now what Alice does, Alice measures her photon. Alice measures the polarization of a photon. And she wants to measure it in the horizontal vertical basis, which means that she needs to have a device that can tell whether the photon is horizontal or vertical polarized, horizontally polarized or vertically polarized. And she doesn't care what Bob does. At the moment she has no idea, no clue of what Bob does. Bob may be alive, Bob may be dead, Bob may be doing his experiment in his own universe. She doesn't know about it and she doesn't care about it. So how can Alice measure the state of polarization of a photon? What kind of device does she need? Polarizer? It's better to have a polarizing beam splitter. It's better to have some kind of device, and we've seen these devices, a PHV device, like a Stern-Gerlach apparatus, which has two output channels, a ket H channel and a ket V channel. Alright, and she has detectors in front of these channels. Let's call this D1, let's call this D2. So this is Alice's detector. These are Alice's detectors. Now if this state has been created, the question first of all that I would like to ask you, if one photon pair has been created, just one photon pair. So one photon comes in, one pair is created, an entangled pair is created, Bob's photon goes into a black hole, it disappears, or Bob is himself in a black hole and we don't know where he is. But Alice chooses to measure her own photon, the state of her photon. Which of her detectors is going to click with this entangled state? It could be either with half probability. Half of that probability is coming from this term and the other half is coming from this term. Alice, for example, is, suppose the first party, this is Alice, the first qubit is Alice, this represents Alice, and the second photon goes to Bob. So this is Bob. The second photon is in Bob's possession. But Alice chooses to measure her own photon exclusively, irrespective of what Bob does. So she has a half probability that her detector D1 is going to click and another half probability that her detector D2 clicks. Now if one were to repeat this experiment, if many photons came in, all of them single photons but one by one, so many entangled pairs would be created, but many entangled pairs would be created one by one. So in each case, if she were to repeat her experiment over a large number of times on all the photons that she receives, half of them will have D1 click and half of them will have D2 click. So from her perspective, the photon that she receives is totally random. She is receiving a kind of mixed state. Half of the photons that she gets are in the state ket 0 and the other half are in the state ket 1. So her outputs are totally random as it can be. You cannot have anything more random than half of the output going to D1 and half of the output going to D2. That's the maximally random state, right? So the entropy of this state, if you know a little bit of thermodynamics, is maximum. It's highly disordered. The uncertainty in this polarization of her photon is maximized. She doesn't know what state her photon is going to be in. Now suppose Bob is lucky and Bob survives. So Bob also has a measurement device. So this is Bob's measurement device, which is totally identical to Alice's. Another PHB. So let me kind of reposition this so that I can draw something else as well. So this is Bob's measurement device, and Bob's photons can also take two output possibilities, and he has his own set of detectors, D1 and D2, now corresponding to Bob. Now if you were to put the boot on the other leg, right, which means now Bob doesn't care about Alice. So Alice is lost somewhere. If Bob were to do his own experiment in his own universe, he would also get half probabilities on each one of his detectors. But suppose both Alice and Bob survive. Both Alice and Bob are up and running, they are kind of energetic, they are far away in the universe, they are on different parts of the planet, and both of them decide to make a measurement. Each one of them carries one of the photons in the entangled pair. Now when Alice and Bob go to their own parts of the universe and do measurements on their photons, so they constantly get a stream of photons coming in. So photons come in, they go to Alice and Bob, another photon comes in, goes to Alice and Bob. So this process repeats. And each time Alice and Bob receive a photon, they do a measurement on their photons. And they're far away, still they cannot communicate with one another. And now they write down their outcomes. So if they were to write down their outcomes, and if this were a purely entangled state, their outcomes will be perfectly correlated. So if Bob's outcomes and Alice's outcomes are compared. So Bob does his own measurements, irrespective, without knowing what Alice gets in her measurement. He does his own sequence of measurements on the photons that he receives. Suppose Bob's outcomes are totally random. H, H, V, 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 H, V, V, H, V, V. So this is a string of Bob's outcomes. And he keeps this list of outcomes, this catalog of outcomes in his own pocket. And Alice, in another universe, with one photon in the entangled pair, she does her own set of measurements. She would get a sequence of outcomes and when Alice and Bob reconvene for Alice's birthday, they get together, travel few light years down and come together and share their outcomes. Their outcomes are going to be perfectly correlated with one another. Perfectly correlated. Now this is a strange thing about entanglement. Alice, in his first run, she could have gotten an H or a V with equal probability, with 50% probability. Bob, in his first run, could have gotten an H or V with equal probability. There's no certainty that if Bob didn't look at Alice's output, his measurement outcome on its own could have been H or V. However, when the two, Alice and Bob, the two parties run their experiments and they compare their outcomes, they're perfectly correlated. All right, I'm going to take questions, don't worry. So this is a correlation between the two qubits. When each qubit is looked at on its own, it appears to be totally random. But when the two measurement outcomes are compared, there is perfect correlation or anti-correlation between them. Anti-correlation I say because if this entangled state were HV plus VH, it would be perfect anti-correlation, but some kind of perfect correlation or anti-correlation exists. So two random objects, each one of them is random, but when we look at them as a whole, there's perfect correlation. So this is the kind of interesting and confounding property of this entangled pair. So now Alice and Bob can be really far off. If Alice makes a measurement and he gets a certain output, say H, if she gets an output H, she can say with confidence, with 100% confidence, that if Bob were to perform a measurement on his photon, which is the twin of my photon, his outcome with 100% certainty would be horizontally polarized. Even though there is no communication between Alice and Bob. There is no secret messaging between Alice and Bob. Alice cannot cheat and send a secret message to Bob and tell him what her output is, so he should change his results. He can say with absolute confidence that if he measures an H, Bob is going to, if she measures an H, Bob is also going to measure an H. If Alice measures a V, Bob is also going to measure a V. Even if Bob does not make a measurement, his photon is going to be in the ket V state. His photon is going to be in the ket H state. So an action at one point in space is going to affect another material object, another photon far away in the universe without any communication between the two objects. So this is action at a distance. So Einstein called this spooky action at a distance. So let's take a 10-minute break and we'll start off with your questions. All right, my dear friends, let's start. Excuse me, बैठ जाओ. One self-made typo that I would like to correct. So this is really important. This is phi. sorry, I made this mistake. This is psi. Right. So if a state phi plus were created, if this phi plus were created, which is one of these two states, there will be perfect correlation. So H will correspond to an H and a V will correspond to a V. If this state had been created, an H would correspond to a V and a V would correspond to an H. So Alice and Bob need to know which of the two kinds of Bell states they've received. Yes, please. There was another question over here. Yes.
BBO crystal. See, those separate photons.
Right. So what generally happens in a BBO crystal, I didn't want to go into this, but generally, if you have two energy levels in an atom, what generally happens is you shine a photon onto this atom, an electron gets excited to a higher level, then that electron de-excites and a single photon is emitted, and the frequency of the emitted photon is the same as the frequency of the incoming photon. The two photons will have same energies. Frequency is energy for a photon because E equals HF. Now this is a normal optical process. Normally most of the optical processes are like this. However, in a BBO crystal, you have an intermediate state. Say, suppose it's roughly in between, and a photon comes in, one photon, it's emitted to an excited state, but then when it demotes in two steps. First of all, it demotes to this middle state, and in quick succession it demotes to the other state. So two photons are emitted, and each photon has half the energy, roughly half the energy, half the frequency, double the wavelength, and these two photons are emitted at the same point in time, and their polarizations are also correlated. If this is ket H, this would also be ket H. If this is ket V, this is also ket V. So this is what happens inside a BBO crystal, and this is a non-linear process. It has a very small efficiency. It happens very rarely. So this is how we generate entangled photon, and this is how we do it in our lab upstairs. I can take one or two more questions. Yes, please. The information has not yet been transferred because in order to ascertain that information is transmitted, there has to be some sharing of information. No information has traveled so far between Alice and Bob, because it's possible that Alice makes a measurement in a different basis, Bob makes a measurement in a different basis. So no postulates of special relativity are violated. Today I am going to discuss quantum teleportation as well, so I am going to highlight this point a bit further. Yes, please.
Can you explain that concept of like what happens during de-exciting in BBO?
So one photon comes in, and when this electron that has been excited, it doesn't jump down to the ground level in one go. It takes an intermediate state, a transitory state. So it comes back to the transitory state, makes a jump from here to here, from A to B, emits one photon, and then immediately from B to C emits another photon. Okay.
So is the entanglement maintained after the measurement is made by the one?
I'm going to talk about this. Yes, please. No, the photon is not split. One photon comes in and two photons are emitted. Yes, please. Which probability? These probabilities over here? Yes, we'll do that. Yes, please.
Sir, the correlation of the output that we're getting, we will still get it if both of them get the experiment at the same time.
It doesn't matter.
So how does it have the significance? How does it matter?
Why? Because it is significant, because Here you're getting a totally random stream of output. So if Alice measures V, she would immediately know that Bob's photon has immediately taken up this character of vertical polarization.
What I mean is that how do we incorporate into things that we are doing? We are not going to travel money.
Right, so we're going to do this. I'm going to give you examples for this. So all of this is not a mere figment of our imagination. This is not an abstract idea, by the way. This is all done and tested, and it's used as a resource in quantum communication, in quantum information, as I'm going to show in a minute. By the way, so one of the really interesting ideas here, suppose phi plus has been created. Let's talk about probabilities here. Phi plus has been created. Phi plus is 1 over under root 2 ket h plus ket v. Now when Alice and Bob measure their photons, there are 4 kinds of outcomes possible. Alice and Bob both measure h. Alice and Bob both measure v. Alice measures h, Bob measures v. Alice measures v, Bob measures h. 4 possibilities. So we can compute the probability for each outcome. Let's do one of them. Let's compute the probability for, say, this particular outcome, V and V. Alice measures ket V and Bob measures ket V. Alice holds the first qubit and Bob holds the second qubit. So how do we calculate probabilities? Where is my Palestine? It's over there. Good. So this is the input state, and Alice measures ket V and Bob measures ket V. So I need to form the bras corresponding to those outputs. So Alice's bra is ket V and Bob's bra is ket V. So I need to form this inner product. The modulus square of this will give me the probability that Alice's output is V, Bob's output is V. Correct? So this is how we compute probabilities. I'll take the modulus square later. I'm just finding the inner product so far. So ket V, bra ket V, and the entangled state, I just write 1 over under root 2 over here. H plus ket V. I'm going to write bigger for the people at the back. So I've just reintroduced the tensor product sign so that things are slightly more amenable to you, more understandable to you. So I need to form the inner product of this bra, big bra with this big ket, this big bra with this big ket. So the first item, Alice's world, talks only to its own bra and its own ket, and Bob's world talks only to its own bra and its own ket. So this is Alice's world, Alice's world. 1 over under root 2 ket bra V ket H. Then bra V ket V. Sorry. So I'm forming this inner product. So ket V, bra V, ket H, and then the second is Bob's world, bra V, ket H. So this is the first term. The second term would be this bra V and this ket V in first location, and in Bob's world this is bra V, ket V. So this just disappears, is 0. This survives. All of this is 1. So if I would then take the modulus square of this, modulus square, I'll get 1/2. So half of the times both Alice and Bob measure V, vertically polarized states for their respective photons. Half of the times they will measure H for their respective photons. You can repeat the calculation putting ket H, sorry, bra H crossed with bra H. With 0 probability, they will get H and V. And with 0 probability, they will get V and H. So half of these outcomes are HH, half of them are VV. But they're perfectly correlated. And remember, our input state were phi plus. If our input state were a psi plus, another Bell state, there will be perfect anti-correlation. So even though Alice and Bob are into separate parts of the universe, totally disconnected in space, in time, but both of them carry one of the photons that have been prepared as twins in an entangled pair, they will have perfect correlation between these results. Alice will measure something, she can immediately know for sure that Bob's photon, if he were to measure it, Bob would get this output. But Alice and Bob need to know that what kind of entangled state they hold. By the way, the really interesting thing, the twist to this story, and why is this interesting? First of all, it's action at a distance, really long distances. You're doing an experiment here, you're immediately changing the potential outcome for the same experiment on a different location, even though on its own, those outcomes were totally random. This is confounding and baffling in its own right. The second really interesting part is the following. Suppose Alice and Bob choose to measure in a different basis. So what does that mean? So instead of a device that kind of shifts between, produces two output channels, horizontal and vertical, what if Alice and Bob agree upon themselves that they would choose in a DA basis, diagonal anti-diagonal basis? What if that happens? So now they are choosing different kinds of outcomes, different possible outcomes. So their experiment is going to change in the following fashion. An entangled state is generated exactly in the same fashion, phi plus. Two photons are produced. They see mirrors just to steer the path of light. Now in this large expanse of space and time, this entangled state phi plus exists. And now this is Alice's world, Alice ki dunya, this is Bob ki dunya, Bob's world. And Alice and Bob decide that they can choose between two different kinds of measuring devices. Alice has the capability to choose between a PHV or a PDA, which kind of creates two output channels corresponding to ket D and ket A. Ket D, I just want, if you would like to recall, is 1 over under root 2 H plus V, and ket A is 1 over under root 2 H minus V. So this is 45 degrees polarized, this is minus 45 degrees polarized. So likewise, Bob can choose between these two different kinds of measurements, PAHV, HV, and PDA. If both of them measure in the horizontal vertical basis, we've already seen what the results look like. The really baffling thing is that if both of them decide to measure in the diagonal anti-diagonal basis, or they happen to measure in the diagonal anti-diagonal basis, there will still be perfect correlation. No matter how, from which angle you look at these entangled states, there is still perfect correlation. So if both of them measure it in the DA basis, there will be in perfectly correlated. However, if Alice chooses to measure in the HV basis and Bob chooses to measure in the DA basis, there will be no correlation. All the correlation will be washed away. Now this I think should be homework problem or a tutorial problem. What if both Alice and Bob measure in the diagonal anti-diagonal basis? You just need to replace the diagonal, anti-diagonal, diagonal terms here and find out what the probabilities are. So now you have an entangled state, totally random. Each sub part is totally random. But when you look at the two random parts in tandem together, there's perfect correlation. And it doesn't matter how you look at it on the two photons. You can look at the photons from any basis, from any choice of axis. If both of the parties agree on a choice of axis, they will still see correlated results. Now I have prepared a really nice kind of infographic. Math and physics is good, but this is a cartoonic representation of what's going on, just to build up your concepts. Suppose I have a vase, and in vase there are balls, and I'm looking at one property, one degree of freedom of these balls, and that is color. I'm concerned with the color. That's my degree of freedom, the color of the balls. This could be polarization of photons, whatever, but I'm concerned right now with the color of balls. You also know very well that artists generally use a wheel called the color wheel. Now I use this example because it's easy to kind of draw analogies between what I've been discussing on the blackboard. So the color wheel is a sequence of colors, and I can draw arrows on this color wheel, and the arrow can point in any of the 360-degree directions, right? It can point in any direction. And on two opposite sides of the arrow, towards the head and the tail, there are two colors. And I mix the two colors, the two colors there are complementary to one another. So I mix them, I'll get probably white, but they're complementary colors. Now the arrow represents the direction in which Alice and Bob choose to measure the color. Now the question I would like to ask is, what color is a ball? Suppose Alice and Bob, both of them, this vase is jumbled, it has many balls in it, it's rolled, tossed around and jumbled, all the balls come in a kind of chaotic fashion, and Alice picks up one ball and Bob picks up the other ball. So there are pairs of balls. So Alice and Bob pick up one pair of balls. Alice runs away with one ball in one direction, Bob in the other direction. And both of them decide that, all right, before an experiment they decide the direction of that arrow. All right. Now it happens that if they have chosen a particular direction of the arrow, if Alice looks at her ball and Bob looks at his ball, both of those balls will, say, be on the opposite sides of the arrow. Now pick up another pair from the vase and run away with the two balls inside the pair and choose a different direction of the arrow. Alice and Bob will still see their balls to be on opposite sides of the arrow. So their colors are totally correlated with one another. But if Alice just does a measurement on her sequence of balls on her own without recourse to what Bob is doing, her sequence of colors is going to be totally random. It could be any color inside this artist wheel. But whatever color she chooses from this random set, that color will be complementary, totally complementary in all cases to the ball that Bob receives. So even though Alice's outcomes on her own, they're totally random, there's a perfect correlation with Bob's colors. Now in this scenario, it's very hard to say what is the color of a ball. The ball in itself, that's why I've drawn the ball in a color neutral fashion. The ball does not have a property per se of color. It's how you measure it, and the objective reality of this property of color no longer exists. That's why the concept of reality is really changed in quantum mechanics. There is no objective attribute of the polarization of a photon. You can't tell the polarization of a photon until you've measured it. So, and the two polarizations in the entangled pair, they're totally correlated or anti-correlated, whatever the case may be. So, this is the whole gist of the concept of entanglement. It's not explainable in any manner by classical physics, and it's useful. It's not a figment of our imagination. I'll give you several examples of how this is useful. It's a resource for quantum computing. It's a resource for quantum physics. We discovered that in our quantum erasure experiment, when we tagged the paths of the photons through the polarizers, the path became entangled with the polarization of the photon. It's a useful resource and it can do wonders, as I'll explain shortly. So now I can take a few questions. Yes, please.
Sir, are you going to understand what's so special in it? Like, हमें ये पता है कि balls pair में हैं.
Balls?
Pair में हैं, you said it right. And we know कि like they is like the balls का color होगा वो opposite होगा. So अगर Alice जाती है और अपने ball को देखती है तो it's obvious कि जो off pass ball होगा उसका color opposite होगा.
लेकिन बिलफर्स सारे पेयर्स आइडेंटिकल हैं. All the pairs are identical. How is it possible that Alice gets a different sequence of color every time? She can only choose between two kinds of colors then.
What do you mean by all pairs are identical?
All pairs identical means all pairs are identical, which really means that all the photon pairs, all the pairs of balls, they are totally identical. This is a quantum state. This is a quantum state. This is a pair of photons. If I repeat the experiment with another pair of photons which is in an identical quantum state, how is it possible that each time Alice gets a different result? In this case, Alice is getting an infinite variety of colors. How would that be possible? It's not possible. This is really, I do not think it's explicable. You have, it's not a multicolored ball. The ball is not all of it at the same time. This polarization here is a superposition of horizontal and vertical, but it also has some diagonal in it. It also has some anti-diagonal in it. It also has all of those other angles in it. So just keep in mind that all these pairs of balls are identical. So it is indeed an interesting phenomenon. It's unexplicable classically. Any more questions? By the way, I have uploaded a reference to a very nice book, 6 Quantum Pieces. Just go through that book. This is a very valuable reading material. Yes, please. Sorry? But they will be totally correlated. So it's random on the parts are random, but the whole is not random. Right. So this is how this is why this object is interesting. Yes. Now, what I would like to kind of argue here is something really interesting.
So it's the same ball, but it's getting different colors every time.
Yeah, you measure it to have different colors. It's not getting a color. You're measuring it to have different colors. The object does not have an intrinsic property called color. The photon does not have an attribute which is polarization. Reality takes a different meaning. Excuse me. Reality is not real. That's what all of this means. There is no objective attribute that you can assign to particles. Now, how is quantum entanglement useful at all? All right, so I want to talk about quantum teleportation. That's a nice usage of quantum entanglement. Before I'm able to talk about quantum teleportation, a small snippet about quantum physics. In classical physics, you can take a piece of information and copy it. You can Xerox, you can photocopy, you can kind of scan things and copy information. It's not possible to do this quantum physically. So cloning is not possible. You can clone dolly sheep, you can clone bacteria, you can clone other things, but you cannot clone quantum information, right? So there's a no cloning kind of theorem. And there are several proofs for this. One proof that is really nice goes as follows. It's a very simple proof. Suppose I have a quantum state that I want to copy onto another piece of matter, onto another qubit. All right. So I have the information. The quantum states carry information. For example, 0 and 1 is a piece of information. If I talk about qubit, the qubit harbors 1 bit worth of information, 0 or 1. So now I want to copy it on some other qubit. So I take a partner qubit, like a scratch register, right? You want to copy something, you need another piece of paper onto which you would like to copy. So this is another partner qubit, which is also initialized in some state, say 0. All right. Now suppose I have that cloning machine, an envisaged जो मैं चाह रहा हूँ, a proposed cloning machine. I envisage or predict that there such a machine exists. So that's going to be a quantum transformation. So I can write a unitary operator for this. So this is the cloning operator, a hypothetical cloning operator. So my argument is that such a U cannot exist. So I am proving by contradiction. Suppose such a U exists. So if such a U exists, what this would do is would take this piece of information and copy it to the second qubit. So it would take this piece of information, the second qubit is just scratch, and I can take this information and put it into the second qubit. So this is what the cloner would do onto this input state. The cloner, the same cloner, if it were a perfect cloner, would clone, if it were to act on this input state, what would the output be? So it would be 1, 1. Now this information is also copied onto the scratch. This is the scratch qubit, the auxiliary qubit. इसको scratch qubit कह दें या auxiliary qubit कह दें. This is just, we need a place to where do we copy information to, right? That's just that placeholder. Yes, please. Yeah, this is the exact copy of this piece of information over here. We don't care about what goes into the second qubit. That's just a placeholder. Now, if such a universal cloner exists, then what should it do to an arbitrary state? So what's an arbitrary quantum state? This is an arbitrary quantum state. Arbitrary means this is the most general form of any quantum state. So it must also clone arbitrary quantum states. Now this cloner acts on this configuration, this 2 qubit state. If this were really a cloner, what output should we get? A cat 0 plus B cat 1 and then crossed with the second qubit. This information is now copied onto the second qubit. Where A and B are complex numbers. Right? So this really is A star 0 0 plus AB 0 1 plus B A or AB 1 0 plus B star 1 1. This is what you should get, right? However, if you look at these two operations and assume that quantum physics is linear, suppose the U clone So isn't this equal to U clone acting on A 0 0 plus B 1 0, right? So this is the same as this. However, if quantum physics were linear and I use these two definitions, then this, if I just use the linearity property of quantum physics and U clone acted on A times this state plus B times this state, I would get A times this state and B times this state, right? So U clone acting on A times this state, A 0 0 plus B 1 0, I would simply get A times this state, A 0 0 plus B 1 1, and this is not the same as this thing. They're different, totally different. Got it? Therefore, such a cloner does not exist. If quantum physics were linear, such a cloning operation is impossible. What at best it can do? At best, it can only copy orthogonal states or basis states. It cannot copy arbitrary quantum states. So cloning is not possible quantum mechanically. However, one operation is possible, and that is quantum teleportation. Now what I'm going to do today is I'm just going to build the circuit, and I would ask you to do this as a homework before the class, before the next class. In quantum teleportation, there is a qubit that you would like to clone. Supposedly you would like to clone, or supposedly you would like to take that information and put it onto another system. You want to clone it. So you're attempting to copy information. So you have a qubit in the state ket A0, A ket 0 plus B ket 1, an arbitrary quantum state. And you also create an entangled pair of qubits. Last 5 minutes, please pay attention, really important stuff. This is a qubit that you would like to copy. Now what you do is you prepare at the same time another pair of qubits, qubit number 2 and qubit number 3, and they are entangled with each other. Qubit 2 and qubit 3 are mutually entangled. So qubit 2 and qubit 3 are in the state ket phi plus, which is 1 over under root 2 ket 0 0 plus ket 1 1. Now this qubit is possessed by Alice. The photon pairs, or the pair of qubits, are generated as an entangled pair. One of the twins in the pair goes to Alice and the other party goes to Bob. So there are two qubits. One qubit is handed over to Alice. Alice, ye lo. The other qubit is handed over to Bob. Bob, tum ye le lo. Now Alice has two qubits. One is the qubit whose information she wishes to copy, and one, the second qubit that she possesses now, is a member of the entangled pair. So now these two kind of channels go to Alice. This is Alice's world over here. This is Alice's world. All of this is Alice's world. The third qubit goes to Bob, far away. really, really far off. This is Bob's world. This is Bob's den, Bob's habitat. Okay. Now what Alice does is she doesn't measure any qubit at this point in time, and she doesn't know what her qubit is. She still hasn't measured her own qubit. So she wants to transmit quantum information, but she doesn't know what the information is. She doesn't measure her qubit at this point in time, because if she measured her qubit, this state will just collapse, it will go away. So what she really does is the following. She does a controlled knot in this fashion. And there's a Hadamard gate on her first qubit. Still she hasn't done any measurement. However, after this NOT gate and this Hadamard gate, which presumably is kind of reverse of what we have over there. So I've drawn the reverse circuit to that Bell state creator. So here we had a Hadamard gate followed by a controlled NOT gate. Here we have a controlled NOT gate followed by a Hadamard gate. And one of the homework problems talks about whether this gate is the reverse of that. No matter what the case is, now she just has 2 qubits. And she does a measurement on her qubits. Right? She measures her qubit. This qubit could turn out to be ket 0 or ket 1. And she also measures a second qubit, ket 0 or ket 1. Now when she's measured her qubits, she gets some classical results. She gets some bits at the output, not qubits. She gets a 0 here or a 1 here, and she gets a 0 here or a 1 here. So there are 4 kinds of outputs she gets. She can get a 0 0 for her first qubit, second qubit, or she could get a 0 1, or she could get a 1 0, or she could get a 1 1. And this is something that you need to show me in your next class. How do you compute the probabilities for these outcomes? Whatever she gets. So these are classical bits of information, a 0 0 0 1 1 0 1 1. These are outcomes. When a quantum state is measured, it gives you a classical result, a bit. Qubit becomes a bit. Now she does a classical communication to Bob. She does a phone call or a WhatsApp message or a kind of satellite link. She sends her outcome, no matter what her outcome is, to Bob through a classical channel. So this is a classical channel, not quantum, nothing quantum about it. Now Bob knows that this is Alice's outcome. So by looking at one of the 4 possible outcomes, Bob can immediately do something to his qubit, and then his qubit will be an exact replica of the incoming qubit. So I would like you to do the kind of quantum state progression for this, and we'll start the next class with this kind of beautiful protocol. Thank you.